Hey, what's Mr. McDonald going to teach us today? Looking like Math Excel. Just kidding. 4.3. Mr. McDonald, take it away.
Thank you. Okay. We are going to start on Math Excel. All right. So this is one of those big temperature problems. Do you remember which formula you're supposed to use?
Yeah.
Remember what it's called?
I don't remember what it's called, but I know what it is.
Newton's law of cooling. Yeah. This guy. All right. So T sub S is surrounding or room temperature. T sub 0 is initial temperature. T of T and little t are a temperature at a certain time that go together. And then remember, K is a constant. With these problems, K is always going to be the first thing you solve for. So let's plug in what we can. In this situation, what is T sub 0, the initial temperature? 65. What is the surrounding temperature? Okay, that's good. And that goes in there twice. Negative K, and then I need a point, a time and a temperature that go together. 50 is the temperature after 1 minute. So now you can go ahead and solve for K. You can just simplify your fraction here. So it's going to be 30 over 45 equals negative K. And then from there, you just use your calculator, evaluate the natural log, and divide by -1. 30 over 45 divided by -1. And I would give it a few decimal places. 0.4055 is the constant for this problem. Okay, so now the first three things it's going to ask for in Math Excel are what's the reading after 4 minutes, 9 minutes, and 1 hour, which are essentially the same problem. You just plug 4, 9, and 60 into the equation for little t, and you are solving for the big T that goes with it. So we'll do just one of them together because they all kind of look the same. We'll do the 4-minute one. It's going to be natural log of, a few things are never going to change. Initial temperature is still 65, surrounding temperature is still 20. K is now a known value. Make sure you put the negative in front of it. That's built into the formula. Negative 0.4055. Here we know the time, 4 minutes. We're solving for the temperature, so I'll just put a capital T there. Is what we're solving for. So a couple things you can simplify. Denominator I can simplify to a 45, right? And it's still T minus 20 in the numerator. And then those guys I can multiply together. I'm just going to use the value I have in my calculator. So that times -1 times 4 gives me about -1.6219. And now this may be the part where you got stuck if you were doing this on your own. I think Math Excel, the hint they give you tells you something about like using a power of E. I don't love that so much because we haven't really done it yet. Instead, I would think of my eraser button. Think of natural log as log base E. If you want to get rid of that log, you write it with exponents instead. So what would this look like with exponents? What would the base be? E. The power would be that guy equals that fraction. And then from there you can evaluate e to that power. Again, I've got that saved in my calculator. So e to that power gives me about 0.1975. And then the last two steps are multiply by 45 and then add 20. So if I multiply by 45, add 20, I get 28.8 repeating, which if I round to the nearest hundredth is 28.89 degrees Fahrenheit. Correct answer. And then you would just repeat the process 2 more times. You plug in 9, you plug in 60, you can see what it evaluates to. Okay, but that K value is going to be the same throughout. Now I think the bottom part is actually easier than the top part. How long will it take for the reading to drop to 23? So again, certain things aren't changing. It's still a 65, it's still a 20. Here you know the temperature is 23, and you are solving for the time. And this is more like the one we did in class together. You evaluate that natural log, so it'd be natural log of 3 over 45, and then you divide by that decimal to get the time. So let's see. Divided by negative 0.4055. And again, if I round to the nearest hundredth, 2 decimal places, I'm going to get 6.68 minutes. Okay. Any questions on that one? Somebody told me that's like the second to the last problem on the homework. So if you haven't gotten there, it'll towards the end. Okay, so just a few little things to wrap up 4.3, then again, this shouldn't take very long. First is change of base formula. I told you guys when we started logs last week that the most important thing you should know about a log is how to write it with an exponent, like we just did in that last problem. This guy is a close second. If you want to know anything else about logs, you want to know the change of base formula. The change of base formula lets you put any log in any calculator. That's important, right? Because you have a basic calculator test coming up. Okay, so this will be useful to you. It says that if I have any log base b of x, whatever those values happen to be, there's a couple different ways I can write it. What you see first here, this is just the general formula. It says log base a of x and log base a of b is another way to write it. This guy's not super useful to us because you would need to evaluate a value for a, which is not something that we have in a basic calculator. Instead, we use the formula more in base 10 and base e, common logs and natural logs, because those are buttons in any calculator. So those are the two I'd probably write down. It does work for any base, which is important to know, but this is the more useful end of it. Okay, if I see log base b of x, it's the same as log of x over log of b, our common log, or natural log of x over natural log of b. So again, that's how I put in any calculator without that log base function. That's what your calculator is doing when it does that log base function. It's just using the change of base formula. That's the programming behind it if you went and looked at it. Okay, so a problem like this, we'll just do one of these because they're quick. If I have log base 3 of 15, remember evaluating that means 3 to what power gives us 15. It's not something you're going to do in your head. It's something you would have to use a calculator for. But it's a different log base than just our common log or a natural log. So up until now, you would need the graphing calculator to be able to do that. So instead, we rewrite it with the change of base property. Two different ways it can be written. It can be written as, this is what it would look like with common log, log of 15 over log of 3, or natural log 15 over natural log 3. And if you want, go ahead and type them in your calculator. Try both of those. Use the log and the natural log button that are on the left side. You'll see that for both of those, you get the exact same decimal. And then you could always type this in your graphing calculator too, using your log base function, and see that they are all the same. Okay, but again, importantly, we would be able to do this on a basic calculator too. You should get like 2 point something. 6. Well, and remember, that's the power we're figuring out. 3 to about that power gives us 15. Okay? Questions on the change of base property? Yeah. Okay, next, we're going to do a couple half-life problems show up in this section. Remember this formula? Kind of looks like our PERT formula. A of t is an ending amount. A sub 0 is an initial amount. K is a growth rate. If it's a positive number, it's growing. If it's a negative number, it's decaying. And then t is some unit of time. Our half-life problems, we're going to use that formula side by side with a formula for a half-life. H is the only new variable that shows up for half-life, and it equals negative natural log 2 over k. The k in this formula is the same as the k in that formula. It's an overlapping variable. So what this allows us to do, if we use these two formulas together, we could maybe put some information in the first equation, solve for k, and then use that to find the half-life. Or maybe vice versa. We could take a half-life, solve for the growth rate, bless you, and then work backwards and figure out, I don't know, how much of the element is left after a certain amount of time, something like that. Okay, so when you do this, you'll use one of the formulas first, solve for k, and then plug k into the other formula to answer your question. And it'll just depend what you're given on which one you use first. So when I do these, I just take both my formulas, I plug in everything I can, wherever I can, and just see what I'm able to solve for. So in this one, an experiment, 100 grams of a radioactive element, strontium-90, decayed to 66 grams in 15 years. Find its half-life to the nearest year. So here's my first formula. Do I know the half-life in this problem? Do I know the growth rate, the percent? No. Okay, so nothing I can solve for here yet. We need the other formula. This is our general growth and decay. Do I know an ending amount after a certain amount of time? Yeah? What is it? I ended with 66 grams. How much did we start with? 100. E is always a constant. K, we said already we don't know that. T, how much time has gone by? 15. And we've solved problems like this before. We actually did it in context with a PERT formula, but it's the same steps. First thing you're going to do is divide by 100. So that'll give you the 0.66 equals e to the 15k power. Next thing I need to do is get rid of the e. Do you remember how to do that? Natural log. If I take natural log of this side, I'm just left with natural log 0.66. Natural log here will cancel out my e. And then last step, divide by 15 on each side. Okay, equals, and again you need a calculator. K should always be a negative number in these problems because it's exponential decay when we have a half-life. I get negative 0.0277. Okay. Now, because I know that, I can put it in over here and I can find my half-life. So you can just use the calculator, negative natural log 2 divided by whatever number you have in your calculator. So you really wouldn't have to round until the end. Divided by my answer. And to the nearest year, I get 25 years. In my calculator, it actually says 25.022. That's what you should probably see in yours, but to the nearest year, we just say 25. Okay. Questions on that? Think you can try one? You feel competent? You can do it? Okay. Try this one. Fill in anything you can in either of the formulas. Okay, so this is what it looks like when you fill everything in the right place to start. So far, so good? Yeah. Okay, now, first thing you should do is solve for k. So 2 ways you can do it. Number 1, you can multiply both sides by k to get out of the denominator, or this really is a proportion. You can make it 14 over 1 and just cross multiply if you want here. 14k equals negative natural log 2, and you end up doing the same steps. Negative natural log 2 divided by 14, whatever that is. Negative 0.0495, and then that goes in for k over here. Now this whole piece is just a numerical value. You can type that in your calculator. E to the, whatever that number is, times 25 power. Let's see. E to that power times, what's 25? So that gives me about 0.29. And then if you divide by 0.29, that's where you're going to get to the nearest gram. If you round that way, it's 97. I think it's like a little smaller than 97, 96 point something. Yeah. Okay. Questions on that? Okay. We just have one more problem to do, and it is figuring out really big numbers. Real quick in your calculator, type in like, I don't know, 2 to the 1000th power. Type it in. 2 to the 1,000th power. What does it do? Overflow. So calculator doesn't do really big numbers. We know it's possible to do 2 to the 1,000th. It's just huge. So we use this property. This is a useful application of logs. It tells us, first of all, how many digits are in a number, and then second of all, it actually helps us write them in scientific notation. If you have a number k, if you find the log of k, and it is between n and n plus 1, whatever those integers are, that number has n plus 1 digits. So let me give you an example of what this means. If I take the log of some number k, and I get 35.37 out, 35.37 is between the integers 35 and 36. It's between n and n plus 1. The number of digits is n plus 1. It's a bigger number. So that means just round up. So k, whatever it is, has 36 digits, is what this property says. Okay, so if you take the log of a number, you get a decimal, we'll round it up, and that's how many digits that number has. Okay. Once we write it in logarithmic form, we can then put it into scientific notation form. So that's going to be our last problem today. This property has to be written with a common log. It is not any log. It doesn't say log base A there or natural log. It must be a common log. We need that base 10 for the scientific notation part later, so that's going to be important. All right, so we're going to do this problem. 234 to the 567th power. Again, if you try to put it in your calculator, it's going to tell you overflow. Calculator is useless for now. All right, so in order to find the number of digits, I'm going to start with my equation, and I need to find the log of this number. So I'm going to take the log of both sides. Now, why this falls into this section is because we use a log property now. I want to take that 567 and I want to bring it down in front of the log. That's our power property from yesterday. So log k equals, it'll be 567 times log 234. And now because I got that 567 out of the power, it's not going to give me any more overflows. Okay, this is what you're going to type in your calculator now. Now your calculator is useful again. Log of k equals 567 log 234. 1343 point, I'm going to write down every decimal I can here, 345391. So how many digits does this number have? $1,300, rounded up, 44 digits. Huge number, right? Okay. Now I want to put in scientific notation. The reason we use common log is because it is a log base 10. Can you write that statement with exponents, like we've been practicing? The base will be 10. The exponent will be what's alone in the logarithmic equation, so this big guy here. Okay, so there's my number written as a power of 10. Useful, but not quite scientific notation, right? Scientific notation has got to be a number between 1 and 10 times 10 to a whole number power. So now the fun trick. I'm going to take this 10, this power of 10, and I'm going to write it as 2 powers of 10. This is actually one of your exponent rules I'm going to use backwards. Back in the day when you did this exponent rule, you had 2 powers of 10 and they were multiplied, so you added the exponents together. Remember that rule? Okay, I'm working backwards. I just need to, if I want to split it, find 2 exponents that will add to this number. I'm going to do it in a smart way. I'm going to pick a whole number, 1343, and then I'm going to use the decimal, everything after the decimal. If I added those powers together, I'd be right back where I started. Agreed? The base would be the same, just our exponent property. Now this is what we want for scientific notation, 10 to a whole number power. And this, because that decimal is always between 0 and 1, 10 to the 0 is 1, 10 to the first is 10. When you evaluate it, it's going to be something between 1 and 10. So you can put that in your calculator. Now in your calculator, my calculator, I still have this guy that I technically have not rounded yet. So what I'm going to do is I'm going to take away the 1343 in my calculator first. And you'll notice that'll actually give you a few more decimal places. And then do 10 to that power. Which that gives me 2.215088853. And that's as much as my calculator is going to give me. Times 10 to the 1343 power. Now this is still rounded an incredibly large amount, right? This number has 1,343 digits, which means the decimal is 1,343 decimal places to the right. So that means there's a lot of zeros at the end of it. So we rounded it a lot, but this is as much as we can get with the calculator. Okay? You can at least get the first few digits of it. And that's it. Okay? Really big numbers. Any questions? Cool. Yeah?
How did you just remove the 1343 in the calculator?
I just subtracted 1343.
Yeah, that makes sense.
Okay. All right. The last 20 minutes are yours to work on math Excel. Tomorrow we'll start 4-4. It's the last section of the chapter. Remember, 4-2 is due tonight, 4-3 is due on Friday.